Good morning to all the participants of IndoMS call. May peace always be upon you. Allow me to introduce myself. My name is Nidia Putriandini. Everyone can call me Nidia. I'm from Airlangga University, and today I'm gonna be the moderator for the session. For today's session, we will continue our activity by having a lecture conducted by Professor Dr. Norhaniza Sarmin from University Technology Malaysia on the topic about topological indices of graph associated to groups. To Professor Niza, the time is yours.
Thank you very much, Nidia,
Yeah.
moderating today. So, Assalamualaikum and good morning. Selamat pagi semuanya. Harap sehat-sehat semuanya. Jadi,
Yeah.
ini kiranya hari terakhir ya,
Yeah.
Zahida.
Yes.
Our last day of the Indonesia Mathematical Society, right? IndoMS, which is actually our second class and our last class. Okay. Are we expecting some more students or some of them are not joining?
Usually they will
come later.
Come later. So you can start now.
Okay. All right. If you remember last class, we went through some of the basics of groups. Okay. If you still remember, you tell me what are the name of the groups. So, Nidia, since you the moderator and the class monitor, everything.
Okay, so the groups are the dihedral group.
Yeah.
Dihedral group, and then generalized quaternion. It's the Q for N, yes. And then quasi-dihedral. Quasi-dihedral is QD to the power of N. Yes.
All right. And we also have 3 graphs, right?
Yep.
Which are?
Non-commuting graph. Non-commuting graph, yes, and C. And then there's the conjugacy class, CC.
Conjugacy class graph.
Also, then the last is coprime, CO, yes.
Okay. Refreshing the memory.
Okay.
Okay, Bu Zaida, Dr. Idayu is here. Ayu, if you can just turn on your camera, if that is possible. Okay, that is my ex-PhD student. She has been helping me with all the notes and everything for this class. And later in the afternoon, she'll be also helping me with the tutorial class. You will be bored with me after 3-4 hours, right? Okay, so it's glad to see you here, Ayu. Thanks. Maybe next time. Last time we went to Jakarta, right? You remember when Professor Dia from Taruna Magara, I think the name of the university, invited. So we went there and presented some of the related research there. There's a conference also. Okay, now groups, graphs, and we have 3 or how many topological indices? The last time we already have 1, right? Remember the winner index. Okay. Now you have to know, I actually went through Dr. Intan's, Bu Intan's, okay, class. Just want to see what she has been teaching you, all right? And I can see that she has covered a lot also about the dihedral group and the non-commuting graph, right? Some of those, and some of the coprime graph a little bit. And I went through also my classes, my lectures, just want to see what you have been seeing from Zoom to see, making sure. That's why I put this dot. There's a light coming in from there. That's why probably you cannot really see this part. But there is one place that I put this. What I meant is actually S6, T6, sorry. So there was a mistake there that I didn't realize. This is the right one. So if you went back and look at your notes, make sure you get this right. Okay, okay for this one. And when I introduced the non-commuting graph, first I write like this. So when you go back, you will put a slash, non-commuting. After that, I mentioned about this, but I realized before I didn't put the slash. Okay, now non-commuting graph, the vertices would be G without the center, right? And two vertices are adjacent if we have this. Okay. Conjugacy class graph, the vertices would be all the non-trivial conjugacy classes. This is the vertices. And they are adjacent if this one is one. Right? So this is for the conjugacy class graph. I just mentioned this because we will be using it again today. And the co-prime graph is the graph. What is the vertices of the co-prime graph? You remember? Nidia? What's the vertices? Don't remember. I will mention it when we went to that. Anyway, today we will go to the second winner index. All right. Okay. Okay, we have 3 classes this morning, right? The first one, we will talk about the Zagreb index, okay? In the second part, we will talk about the, okay, so we have first already this. The second index will be the Zagreb. And this one, the third one will be the Zagreb. And the last one will be the Harari index, okay? Okay, so this already done in the last class. If you remember, we counting the distance, right? The double sum of the distance for each of the vertices, that is the winner index. Now, for the Zagreb index, we have first Zagreb index, and we also have second Zagreb index. All right. So still, our graph has to be connected. Look at the definition. Okay, let this be connected. And the vertex. I already uploaded actually last night the notes. You see it, Nidia? Yeah? All right. Okay, so the vertices of this is 1 until n. Okay. Now the first Z-graph index. We call it M1 of the graph. Okay, this is the sum of the degree of each vertex square. The sum of the square of the degree of each vertex. So V is for all V. Okay. Last time we look at the distance, right? This one we look at the degree. And how do you define the degree? Last time we already defined the degree is how many edges connected to that particular vertex, right? And the second Z-graph index okay. Ibu Zahida sudah share di chat ya. Okay, M2 okay, this is the sum of the product of the degree. The sum of the product of the degree of two vertices for each edge. Yeah, degree of U, degree of V, and UV is in the set of the edges. CC, right? Edges. Yeah. Okay. For each of the edge, we have the two vertices. So you have to multiply. Then take the sum. Okay, it's senang ya. Senang, mudah.
Yeah, mudah.
Mudah.
Senang here, happy.
Oh, senang, happy. Okay, mudah. Easy.
Yes, easy, mudah.
Okay. So next will be the example, right? We will calculate this. Okay, so example. One, two, three, four. The first edge, the second edge, the third edge, the fourth edge, and the fifth edge. So this is just a simple connected graph. So compute the first and second Z-graph index of this. Everyone has breakfast already? Nidia, what do you have for breakfast?
I have porridge, chicken
Porridge.
porridge. Yes.
That's nice. When I went to Indonesia last time, even the breakfast is quite heavy. You know, I remember when I went to Dr. Idayu last time, she really enjoyed the food in Indonesia. Right, Dayu? Looking for all the sambal hijau, sambal merah, really the pedas-pedas one, I cannot stand. So whatever sambal, I will pass to Dr. Idayu.
Actually, I'm grabbing nasi kandar.
Nasi kandar in Penang.
Yes.
This morning I had lontong. Lontong is actually soft. I'm not sure if you have it over there.
Yes.
Yes, we have it.
Ah, I also like gado-gado. That is my favorite.
Oh,
I'm talking because I'm waiting for you to find the solution.
It's currently computing right now. Wait.
Yeah.
Ayo kerjakan itu.
Ini cerita pasal makanan ya. Okay, so M1 of the gamma, writing out the formula. Okay. Now, if I use I as the degree of the vertex, yeah, just to see the index. 1, 2, 3, 4, right? So we have the degree of the first one. What's the degree? 3, right? 3.
Squared. Yeah.
Second one.
2. 2 squared.
The third one.
3 squared.
And the fourth one.
2 squared.
So, mudah ya?
Iya. 26, yes. Oh, 26.
Okay. Now we go to the second one. Little bit longer than the first one. Boleh padam ya?
Yes.
Padam.
Okay, so it's the sum of the degree U, degree V, in which UV is in the edges. Okay, so we have to choose, like for every single E. So for example, with this E, right?
Mm.
E1, you have to choose degree 1 and degree 2. That will be 3
times 2.
And E2, 2 times 3.
2. Which one?
E3,
3 times
3 times 2. E3
Yeah.
is 2 times
2 times 3.
E4,
3 times 2.
E5,
3 times 3.
3 times 3. The answer is
24, 33.
30. Okay, mudah.
Yes.
So
Mudah.
try to visualize what if it's a complete graph, right?
Oh.
The complete graph, you know how many vertices, how many edges in each of the edges, you know the degree, right? So you
Yes.
start thinking about, say, it's 4 for Kn, the degree of the vertices, we know it's
N minus 1.
right? And then you have how many vertices, that will be n vertices. So while we are looking at new definitions, coming up with an example, you always have to think of what kind of properties that you can think that you can have from this any new definition. So this is what we call research, yeah, Abu Zaida. And then we try to find problem. Our problem, mathematic researcher, is to find problem.
Yes.
If there is no problem, it is a problem to us. So that is what we do. We find problem. All right. So I have covered this, and then we are interested to see and to find the indices for all those graphs associated to the groups that we have, right? Okay. All right, so let me write this lemma. This lemma actually will be used in the theorem that I'll just state this, then you can see what kind of preliminary result that you need for our proof later. So I call this lemma 1. So this is regarding the first group, which is
Dihedral.
so let G be the dihedral group, and we start with D6, yeah. And also I have mentioned about this, and also Dr. Intan also mentioned about the centralizer, right? Okay. And the centralizer and the order, the sum of the order, sum of the square of the order of the centralizer, when we take out the center, again we have to separate into two. One is when the case n odd, and another one when the case n even. Okay. And this is equal to n cubed minus n squared plus 4n, n cubed minus n squared. How do you say this in Indonesia?
N quadrat.
N
Quadrat.
Okay.
Yes.
When I listened to Dr. Intan's lecture, so I tried to learn a little bit of quadrat, yeah. Okay. So now you can see why there is something like the sum, something with the square, right? It's very close to the definition of the index before. So this is quite interesting result in which, given the n, n-gon, n-cis here, for the dihedral, you can use that value of n to get this summation. So this depends on n, when n odd n, n even.
And even.
Yeah. I'm not going to go into the proof, but I have already given the proof in the notes, right? You can go through. So in the case in the future, if you do something or research related to this and you want to get this kind of result, and how do we get to get this result, then you can see at the proof. This related to also about the centralizer of the elements in the dihedral group. Which one commute and which one do not commute with the rotation and reflection, yeah? Okay, lemma 2, again we have let G be D to N. Okay, and the same thing, yeah, CGX is the centralizer. Now, the second Zagreb, we have the product, right? So you have the product of these two centralizer whenever we have xy in the edges of the graph. Okay. So this is equal to 2n, n squared minus 1. Again, we have to separate into two cases. And for n squared minus. Okay, so later on, we're trying actually to generalize, okay, the result for this Zagreb index. Okay, and the proof goes to finding the relation in between the centralizer and the edges. So you can go through step by step, pretty clear for this one. So let's look at the first result of Zagreb index for those graphs related to dihedral groups. So the Zagreb index of, I just put here, non-commuting graph, all right? So the first I call it proposition 9. Okay, so I just write this out. The first Zagreb index of the non-commuting graph for any finite group G the first Zagreb index of the non-commuting graph of any finite group G is equal to, for any graph G finite, we can find the order. Okay, finite is, how do you say finite in Indonesia?
Berhingga.
Terhingga. Okay,
Berhingga.
terhingga. Okay, not finite, yeah, not finite.
Infinite. Yeah.
Infinite. Okay, so the order of G squared times the order of G plus the order of the center, okay, minus 2 times the number of conjugacy classes. Okay, so the order of G squared times the order of G plus the center minus 2 times the number of conjugacy classes minus the order of the centralizer square. And you see, this we got before, right? You can plug in later to get the answer. Okay, and for the second Zagreb index, okay, I didn't say about any group. I just mentioned about the finite group. Then you see, you can put in any finite group later. Okay, so the second Zagreb index of non-commuting graph of G is given as negative the order of G squared, the order of E edges of the non-commuting graph plus the order of G multiplied by the first Zagreb index of this. Okay, multiplied by the first Zagreb index plus the lemma that we found before, CGX CGY. Okay, XY in E. So again, if we want to find this, that is why, since we can figure this out from the group, we can find the number of edges from the graph. We can find the order of the group again. We already counted the first Zagreb index. So this is the part that we need from the previous one for particular group that we want to find. Okay, so you can see where we are going and how we can get the first Zagreb index of the non-commuting graph for D2N. All right. You don't actually have to copy this because it's there, but sometimes when I was a student, I want to see my own writing, so I will write. Betul ya?
Yeah, but we write it after the class over.
That's true. Because reading math is really different from doing math. You cannot read math. You have to do math. So that okay, boleh faham, okay boleh ngerti ni semua.
And for me, I cannot write and listen the explanation.
Yeah, that's why we just look and listen and understand. Then after that, because you already have the notes. But sometimes during class, if we don't have any notes, how do you actually want to understand at the same time by copying and writing, right?
Yeah.
But now we have Zoom, we can screenshot, so that's a good
After
thing. I
that,
don't want to say
you write the
pandemic is
notes.
good, but something good out of the physical class. Okay, so our first theorem. So this is of the theorem. Okay. How many of you here are undergraduate? S apa? S1 ya?
Satu.
S1. Undergraduate.
Coba raise hand.
Raise
Yang
hand, raise hand.
S1.
Oh, this morning I forgot to ask everyone to turn on the video to see the face, right? The morning face. S1, S1. S1 angkat tangannya, jarinya. Okey, ni dia S1. S2. S2, S2 tak ada satu.
Ada.
Ada few ya. S3.
S3 looks like they ask permission.
S3 is PhD,
Doctoral.
right?
Yes.
S3. Okay.
Yeah.
So most of you are S1. Okay, S1, S1, and then master, you probably are interested to do PhD. Yeah. Bu Zahida boleh ambil jadi penyelia. Dr. Idayu here, she was my student in S1 for the final year project. And then in UTM, there is a special program which is called fast track. So if you get a first class student in S1, you can go to S3. So Dr. Idayu went from S1 ke S3. And then she finished recently her PhD, submitted in 3 years. So later on you ask Dr. Idayu for the secret. You can ask her email from Bu Zahida.
Okay.
Okay. Oh, right. Theorem, yeah. So M1, the first Zagreb index of the non-committing graph of dihedral group. Okay. So this is n 5n minus 4 n minus 1. So we have to have again two cases here, n odd and n even. And 5n minus 8, n minus 2. You will see later when we have the conjugacy class graph in which we have to break this into another two cases. Do you remember? The one when it's even, n over 2 is even and n over 2 is odd, right? So there are more cases for that one. So you see, you given me a dn, d2n. So using just that order n, you can figure out the first Zagreb index. Okay, and the proof is quite straightforward. It uses the previous proposition and plugging in from the lemma. Okay, you can after this you use that proposition that I share, and also from last class I share about what is the order, right? What is the center? Plug in those proposition and the one that I shared today, and also the lemma, all the numbers, including n and the factor, right? Then you can figure out this. It's quite straightforward. So sometimes you want to prove something big, you break up into smaller case, and then you just plug in. Okay. So I think that is straightforward. Zahida, I'm sure they can follow through and do that proof. Okay. The second one, when we have time, sometime today, I will try to see to show the proof for at least one. Yeah? Okay, I just want to show you the steps because by having all those formula before, and I'm sure all of you can just plug in the one that we have before. You see there is the center, there is the order. So based on the proposition and lemma, you follow and then you plug in, then you get the solution. Okay, now this one is M2, non-commuting graph of D2, right? The second Zagreb index. Also, we have into two cases. And this is with all the square, right? Okay. When I began the class, I mentioned about the boiling point in which the indices are used by the chemists. And in many cases, the chemists actually use some results from whatever mathematicians have found in some of the places. In some others, they really need to do in the laboratory. So in some cases, you can actually compute it faster and do it theoretically. But there is another research of mine which has something to do with biology. So we do the computation in, it's a little bit about DNA computation and splicing system, in which we really want to see how this is done in the lab. It took so much time to get the result that we can actually already predict theoretically. So this is quite interesting. Okay, so this is the result for the hydra. Right, now I want to share about the Zagreb index of conjugacy class graph for dihedral. Correct. So we call it theorem 3. I can erase just that, you cannot. You have to rewrite, right? So that's why I like this whiteboard. Conjugacy class graph of G. Okay, this one, or we use the result from the winner index. Okay, it turned out that this is N times the winner index of this. Okay, all right. Okay, so let me try and prove this one. If you remember the winner index of the conjugacy class graph for the direct group of 2n, that was from last time. All right, it's K, right? The winner index is K. That's something in the bracket, right? Kg minus center, right? The yeah. IU is here. If I make a mistake, you can easily let me know. Okay, so this is from the first class. Okay, so we want to, okay, what is N? N in this case is 4K, yeah? N is 4K, right? N is 4K. Okay, so this is what we want, right? Let me see how we are going to prove this. Okay, so based on proposition 2, you have to recheck this proposition. The number of conjugacy classes is, so we have the case when n is even, and n is even, the number of conjugacy classes is n plus 6 over 2. Okay. And from theorem 2, we have two cases, yeah, for n even and n odd. So for the n even, the Wiener index of the conjugacy classes of D2n is equal to n over 3. Okay. Now, from proposition 2, also the total number of vertices, for the conjugacy class graph for D2n is equal to n plus 2 over 2 when n is 4k. So with all this information, you want to find now the first Zagreb index of this using the formula in which this is the degree, right? Degree of, we call it I squared. Okay. I from 1 until all the number here, n over 2, n plus 2 over 2. And n is even, yeah? When n is even, this one is even, this one is n integer, right? You can divide by 2. Okay, so this is the degree squared of 1 squared, degree of 2 squared until degree of n plus 2 over 2 squared. Now, for this particular one, you have n plus 2 over 2 of each of these is this. N over n plus 2 over 2 minus 1 squared. Okay, because each of those has this degree, n plus 2 over 2 minus 1, right? Okay, so so this is given to be k of g minus the center. You can rewrite this. Okay, this is minus 2, so you have n over 2 squared. So this, which is 4k squared kg minus, okay, which is equal to this. So you see that for this particular conjugacy class graph, the first Zagreb index is related to the Wiener index. All right. Then, okay, this is already in the notes. Okay, you can look again. But this is how you do it step by step using the definition, right? When we do this, of course, for research, you have to do this first. And then you figure out where is the hole, right? The hole is looking at the detail and get the result or the formula for the little one. Take that out and bring it in front, call it like lemma or proposition. Then you plug in, right? Then I want to give you the next theorem. Is the second Zagreb index of D2n, which is also related as before to the first one, right? N over 4, M1. And for this one, we restrict, like before, that this is the case when n is 4k, yeah? theorem 3, if I miss to write it out, I just mentioned that the n that we do is when n is 4k, a multiple of integer, not for the odd one, for the D2n. And the same thing for this one. This is the one that we can generalize. Okay. How do we prove this? Is by using the definition, okay, the sum of the degree of the edges, right? All right, let me move on to the first Zagreb index of co-prime graph. Oh, I can just do this. Co-prime, that's like cheating. For D2n. So the first case is when n is odd. N is odd. Yeah. So I call this 5 and 6. The first Zagreb index of this is equal to n 2n squared plus 5n minus 5. Okay, so G is the ladder group, and for n odd prime, the first Zagreb index is this, a polynomial of degree 3. Okay, and go back to looking at the co-prime graph of D2n when n is odd prime is multipartite. Now I know Indonesian language. The multipartite graph, multipartite, K1, n minus 1, n. Okay, you can go back and look at this. So we have vertices of certain degree in the multipartite graph, right? With degree to n minus 1, with degree n minus 1, n plus 1, and degree n. So just plug in the degree in the summation. Okay, that is pretty straightforward. You have the sum of the degree squared for all those I from 1 to n. So plug in the degree from the multipartite into the formula. You will get this directly right away. Then for this one, okay, so for this one, this is only for, it depends on our graph. When we have to go back to see the graph from the previous lecture from before, it depends on the n. Some of the graph, we can only find the general one for certain n. So for this one, n is 2 to the k. For this particular one, we can generalize this. So I still go to the first one, yeah? So I want to go to the first one first. Okay. Let me change here. So just now it's odd, now it's 2 to the k. So for this one, this is 2n minus 1. Okay, in some of the cases in which we have dihedral with just any even number, because 2 to the n does not cover all even, right? Like 6, it does not cover, that one cannot be generalized. So we have to restrict this depending on the graph that is also connected, right? If the graph is not connected, because we have to have the connected graph in the first place. So you have to go back to the definition and see for that one. Oh, I have only 1 minute. Yeah, Nidia?
If you want to continue, it's okay.
It's okay.
Okay, I'll just finish a little bit because only first and second Zagreb index of co-prime. And we can take a 5-minute break. You need to go to, what do you call the restroom?
Toilet.
Toilet. In Indonesia, you call it?
Kamar mandi.
Itu untuk mandi.
Toilet.
Toilet juga ya. Okay. Let me go for this one first, yeah. Okay, this is 4n is 2 to the k, right? And this is direct from the definition, okay, to find the first Zagreb index. Okay, now let me go to the second Zagreb index for the first case. And odd. Okay, so M2, D2, C0. Okay, this is n to the 4 plus 4n cubed minus 3n squared minus 2n plus 1 is polynomial with that degree 4. And for this proof, because we are looking at all kind of edges, so you have to look at the edges of the graph, and then you find the degree for each of the edge, the degree of the vertices, and then you multiply, and then you sum up. Yeah. So these are all involving the n. When n is 2 to the k, okay, so for this one, it's equal to 2n minus 1 squared. This is the second Zagreb index of the co-prime graph of D2n. All right, so that's the one that I want to show for the Zagreb index. And you remember we still have the other groups. Yeah, we still have the other groups. So I have covered for dihedral for the first and second Zagreb index for the three graph for dihedral. All right. Then you also have results for the Zagreb index, first and second Zagreb index, for the second graph, for the third graph, co-prime we did. Okay, for all graph, for generalized quaternion group and quasi-digit group. All right, that is a whole set of results. I'm not going to go into one by one because the routine is very, very similar. But you can see the results are given as in the notes because I want to cover at least different indices, right? So you can see the pattern now. You can follow through and you can do it for the different graph for the different groups. So I will stop here and we'll come back 10 o'clock your time in 7 minutes. Okay? Yeah, Bu Zahida?
Yeah.
Okay, all right, Bro.
Right. Okay, before that, before I forget, can we just see everyone's face 1 minute?
Ayo on kamera.
Ya, mungkin teman-teman bisa on kamera sebentar.
Apakah sudah ngantuk?
Nanti ada 5 minit lagi. Boleh stretch. Okay. Bangun jalan-jalan. Pergi dapur minum air, biskut. Are they all at home or in campus?
Oh. Kamu mute kan?
You're all at home?
Yeah. Yes.
Ya, semuanya duduk di rumah.
No, it's a boarding house.
No,
okay. It's a boarding house.
Oh, okay. All right, okay. Just look at the camera. I'll take just one shot. Okay, so jumpa lagi 6 minit. 5 minutes is very, very, very fast. Time flies very, very fast. Okay. Okay, so we are done with 2 indices. Now we go to the third indices. Yeah. Okay, the Zagat index. All right, the Zagat index. Okay, now still our graph has to be connected. So if we apply this definition to find the indices for any graph or certain groups, even you don't have to connect with groups, but you can still get graph. But in my research, in our research here, we try to associate graph with groups. So when we apply to find some graph related to groups, and some of these properties of graph really depending on the properties of groups. You won't get the such thing as a conjugacy class graph if you don't have groups, because you need the conjugacy classes from the groups to form the graph, right? But then out some of the graph, they are not connected. So you just choose the cases in which they are connected. And that's why in our result, you will see there are different cases in certain of the results, because those are the one that is, the graph is connected. So again, this is a connected graph. Okay. And we have the vertex set as before. All right. Now the Zagat index, we write like this: S Z index is the sum. All right. This sum is related to the edges, right? Let me see. N1 of E given this, and 2 of E of the edges in gamma, in which the edges is in this set. Okay, so the edges, yeah, the edges. Now, what is N1 and N2? Okay, now N1 E gamma is the order of the set of vertices of the graph in which the distance of this vertices V with X in the graph gamma is less than the distance from V to Y gamma. I will explain what this means. Okay, let me write first. N2 E gamma is equal to the number of these vertices in the set of vertices, and Vy. This is less than Vx. Okay, I need to close this and get the order. Okay, this is the whole set of V. So V is a set of vertices with this distance. as the condition. Find how many that vertices in the set. So what does it mean? N1E gamma counts the vertices of gamma lying closer to one endpoint X of the edge. E then to its other endpoint Y. Okay. And every time looking at the example is much easier to understand, right? Than understanding the definition.
Yes.
What is this? What are you talking about? What is this E? N1 and N2. Okay, so the point is we are counting the number of vertices that satisfy this condition. Okay, and then by the example, I will explain to that one. Okay, so looking at the distance. All right, so let's look at the same example. If I have many whiteboard here, last time I went to a class where there's a whiteboard. One is a whiteboard, right? You can just pull up and pull back down. So
Sliding whiteboard.
whiteboard there. Or I had been to a classroom in which 360-degree, they're all whiteboard. So I can just rotate all of you. But here we don't have that, so I had to redraw the same graph, yeah? Okay, it's okay. So again, 1, 2, 3, 4. The first edge, the second one, D3, D4, D5. Okay, so we want to compute the Z index. Okay. Now, the first one we have to find the edges, right? For the edges. So let's see for the edges E1. Okay, and E1 is this one too. All right, this one too. Okay, so I will erase this first. We will write later. Okay, so N1, E1 gamma. Okay, so we are looking at the X in the vertices in which dx1 is less than dx2, right? The edges here, you want to find the X, right? This is what I mean by the edges for the gamma, right? The edges in the gamma. I should have used V here, but you know what I mean, right? The X here is this V here. Okay, the X here is, all right. Okay. So find the X in the set of vertices. So Ketua kelas Nidia, what is your set of vertices?
The vertices 4.
Yeah, all the vertices.
Oh, 2, 3, and 4.
Okay. So you know that this will be 1 from inside this. Okay, you have to choose in which the distance of x from 1 is always less than this distance from x into 2. So if you put in 1, if you put in 1 here, the distance from 1 to 1 is 0. The distance from 1 to 2 is
1.
1. Is 0 less than 1?
Yes.
Yes, so you can put 1.
Oh, okay.
Ah. Now
Starting to understand.
you check 2. If you put 2 here, the distance from 2 to 1 is 1.
1.
Is it less than 0?
0. No.
So 2 cannot be.
Mm.
Okay.
Mm.
Next one is
3.
The distance from 3 to 1 is
1.
from 3 to 2 is
1.
It's not less.
Yeah, it's
So
equal.
don't put the 3.
Oh,
Okay. Next
okay.
one is
4.
the distance from 4 to 1 is
1.
from 4 to 2 is
2.
2. 1 is less than
2.
so
Oh, okay.
but this is not this, but this is the
The, yes.
order is equal to
2.
2. Okay.
Oh, okay. Yes.
But you have to do this for all the edges.
Mm-mm.
This is only E1.
E1.
You have to do E2, E3, E4, E5.
5.
Okay.
Oh.
For each of those, you have to figure out how many, right? For
Okay.
each of these values. So you have to do it 4 times for each of the
N1 and N2.
yeah. And then you have to do for N2.
Okay.
It's fun, right? Okay. So let's do one of N2. It is not it mudah tapi leceh. Leceh apa? It's very
Complicated or a
No,
lot
no,
of
no.
complicated. It's straightforward, but it's renyah or remeh. That is how we say it in Malay. But you have to do it so many times. You have to check.
Okay.
Right?
Yeah. Harus rajin. Rajin.
Just to have this, but it's not difficult, right? It's simple. You have to really.
But we have to do it. We have to count it.
But when you are already used to it, you can just look at it and choose, right? You can just see the distance. Because it's like routine, right? It's like routine. So y in B gamma, dy1 bigger than. Before it's less than, right? One is bigger. Okay. So it does not mean that this is the complement of this, right? But it's the one that is not equal to.
Yeah.
You remember just now when we calculated, when you do 2 here,
only 2,
right? You get 2, 1 is 1, and 2, 2 is 0. So this is the one because we can flip 0 and 1. So this is actually 2. So the answer is 1. The one which is equal last time, it won't be in both N1 and N2. Okay. So this is really hard to explain, right?
Yes.
But somebody has to explain that, right? Okay, so for this one, if you calculate that for all of the edges, you will get as given in my notes that the number here is 2, 1. For E2, it's 1, 2. So for E1, EI, 1, 2, 3, 4,
5.
you have N1 and
N2.
For E1, just now we have 2, 1. For N1 and N2, is 1, 2. All numbers because it's the number of the element inside. So this is 2, 1.
Is
1. This is also 2, 1. Okay, and the last one is 1, 1. Okay, and so we can find this to be N1 E1 I. This N2 I. This I1. What?
E2.
Okay, oh, I have to find someone to take my photo. Give me 1 minute. Okay, so you just plug in, right? So you go from E1, E1 and N1 and N2, you multiply, right? You multiply. So 2 times 1 plus 1 times 2 plus 2 times
2
1
times 1.
plus
2
2 times
times 1.
1 plus 1.
1 times 1.
4,
6, 8, 9.
9. So this is equal to 9. So this is the second index that we have for this particular graph. All right. To calculate. So this is the critical one, right? You calculate for each of the edges. So you imagine if you have like 10 edges, then you have to check and it satisfy this distance. So now, as I mentioned earlier, now you can think about what if it is a complete graph.
Yes. Okay.
What do you think? Because for the complete one, like this, right? You see, what do you see? The distance from
It's
this.
always 1, except if we choose x as 1, x or y as I mean like as the vertex itself.
Yes.
So it will be 0.
Yeah. So that's the only one that is less. If you have 1 is 0, the other one is 1, right? So this is something like you can think in general, which is
Yes.
the specialties about complete graph. And then you can come up with like, this is a special theorem for complete graph. This is the index. That is what people have done it. They think about just one particular one and then this. So if Nidia, you probably want to further for PhD, right? You can introduce maybe a new index.
Okay.
Even some of the researchers put their name to be there, like a theorem, right? Then okay, so
Can I have a question, Professor?
yes.
So it seems like the way we choose the x and y is depends on the labeling of the vertices.
True.
Because when I count the E2, I was confused for a moment of why the N1 is 1, but then I realized the X is actually true 2 and then the Y is 3. So the distance for the vertex 2 supposed to be lesser than the vertex of 3. So
Yeah.
how do we determine actually which one is the lesser and which one is more? Like, how do we choose the vertices?
This one is at random. It depends on where you label.
Ah,
So
okay.
it doesn't matter. This, your E with your friend's E might be different,
Mm-mm.
but the answer will be this. In any
Ah,
way you do it, even you interchange the X or the Y, which
mm-mm.
one, this one or this one first, even if you put this is 1, 2, 3, 4, right? But
Mm-mm.
actually, because numbers, they're all commutative, that's
Ah,
why
okay.
it doesn't matter. It's a good question. Okay.
Okay, thank you.
All right. Okay, let's look at some of the results for this, since now you have understood the calculation, right? Okay. Okay, so we have to calculate this for 3 graphs, right? For 3 groups, there will be 9. But let me see. Okay. You can also check and think about how these indices are interrelated. The winner last time, we are counting, right, about the summation for the winner index, about the distance. This one is also about the distance, right? So they probably are interrelated. They have, when I say connected, connected is graph connected, but they can also be connected in English connected. They have a relation in between. But let me just write out the result, right? Okay. The Zagat index, when we have dihedral group, yeah? The Zagat index of the non-commuting graph of the dihedral group when n bigger or equal to 3 is equal to n minus 1, n minus a half, 2n, n minus 2, n minus 1, n odd, n even. Theorem. If you see something is missing in the proof, probably we miss a bit about which proposition. That is like proposition. We probably missed them if we didn't. You can figure that out, yeah. So the proof for this is by using the definition and then looking at each of the edges in the graph. All right. I think you can follow through that proof also. It's quite straightforward. Now I go to the second one, theorem 22. This one for the, this one is for this 2n. This one is conjugacy class graph. We have to have 2 cases, right? So this one is when n even, n over 2 is also even, right? Okay. This is n plus 2 over 8. I will put here, yeah? This means like if n is 4, n is 8, right? N is 12, right? Cannot be n is 6, then 6 over 2 is 4. Okay. This is the Zagat index of the conjugacy class graph, right? We're still in the end. Okay. Next one is theorem 23. Okay. Now we go to the coprime graph. Okay. And for this one is an odd. And again, why we have these cases, it depends on the graph, and look at only the connected graph. Okay, this one is n to the 4 minus 2n cubed plus 3n squared minus 2n plus 1. Okay. We have to figure out which vertices and which one is closer in terms of distance, and to compare for each two. And you have to figure out in general for this one because it's n. Okay, now, okay. For the case n 2 to the k, right? We call it okay. So for non-commuting graph, we always have this odd and even. For conjugacy class graph, we have this, right? And for co-prime graph, we have odd and 2 to the k. So this is the okay. Now I want to look at the Zagat index of the non-commuting graph of a different group, the generalized quaternion group. Okay, so we will have, sorry, you have to copy everything. I just can delete. I can just delete this. Right? Okay, so for the first one, for the generalized quaternion group, okay, it's a little bit different. So you look back to the generalized quaternion group, okay, then you look at the three different graphs, right? The non-commuting graph, the conjugacy classes, the conjugacy class graph, and the co-prime graph. Then you look at the different cases. Okay, it's the cases are different than the conjugacy class, right? This one is from before. So for this one, we just have one answer, 8n, 2n minus 1, n minus 1. Okay, with no cases for this one. So the generalized quaternion group Q, 4n. The Zagat index of the non-commuting graph of the generalized quaternion group. And how do we get this is from the results from before, from the graph, okay, the non-commuting graph of the generalized commuting group. It's a multi-partite graph, okay? And you have the sets that n sets have only 2 elements, and another set that has 2 n minus 2 elements, different vertices for this one. So you can see which one are the one non-central, and you see how many edges connecting in general. So you go one by one and see and follow, and then put in back in the formula, you will get for this one. It's quite straightforward. Okay, now we go to the generalized quaternion group, and we go for the conjugacy class graph, right? And when the case and even, okay, when the case and even, we have this U O N, the conjugacy class graph, and n plus 1 over. Okay, now if you look back in proposition 12, okay, the conjugacy class graph of the generalized quaternion group when n is even is complete graph. It's a complete graph of n plus 1 vertices. How many edges then? You know a complete graph with the vertices? How many edges?
If the vertices is n plus 1, then the edges is n.
Edges or vertices?
If the vertices are n plus 1,
Mm-hmm.
then the edges will be n.
The edges, okay, like right? This
Oh,
is
wait. I'm sorry. It should have been n times n plus 1 divided by 2.
yeah.
Okay.
So for a complete graph of n plus 1 vertices, the
Mhm.
degree is n, right? The
Oh yes.
degree is n.
Uh, that's my bad.
It's okay. So the edges will be this many edges. Okay,
Mm.
like I mentioned to you before. So you know all the n1 and n2 is equal to 1, right? The n1 and n2, if it's not itself, is equal to 1. So that's why this is just equal to this. You can figure that out.
Oh yes. Okay.
Okay. Now, so we have in general, not only, but because the conjugacy class graph of generous quaternion group turns out to be a complete graph, so we can easily use the general formula. Okay, so you can write out a complete graph. This is this. Okay, next is when the generalized quaternion group, okay, of order 4n for co-prime graph, right? Okay, for co-prime graph, and we have this for and yeah, we have this only for n 2 to the k minus 1. Okay. All right. So this is equal to 4n minus 1 squared. 4n is 2 to the k minus 1. Okay. The condition depends on how you want to find for the graph that you have. So you have to look into different cases. Is it okay when you're putting k started from 2 or 3 or 4? Do you want it to be just the non-abelian groups and so forth? That is why we putting different conditions depending on the graph. Okay. Now we still have the last group, which is called the
The group or the graph? Wait.
the group, the
The
group,
group. Quasi-dihedral. Dihedral.
group, which is
Q D 2 to the point of to the
to the n,
n.
right? So 8, 9, 10. Okay, so I have to change all the. Okay, you should have actually the group that, not the group, the graph, and then you can see, oh, this is connected for this particular n. Oh, this is not connected. That's why I had to choose this. Okay, so for the first one, you see, even the group is much more complicated than the other two. So the Zagat index for this non-commuting graph, and because of the order, right? Because of the order, it's something with a power 2 to the n. The others is like just 4n, right? Of 2n. That's why the result I put down here, because it's quite long. 2 to the 3n minus 2 minus 3 times 2 to the 2n minus 1 plus 2 to the n plus 1. So even to get this answer to be a little bit complicated, you can imagine to find the proof, right? So from proposition 9 from the last class, you have how many edges of the graph, and then you find which elements are closer to the vertex, whether it's less or whether it's bigger, figure out for the rest of all those edges, then you can just plug in using the definition of the Zagat index, and then figure out, because there will be so many 2 to the power, so you just have to use your factoring power, right? Your own power by factoring and solving this until you get the final one. Okay, now this is for the first one. For the second one is conjugacy class graph. Okay, this is for that. And I have this for order 2 to the n. For this one, yeah. This is the order of G is for the whole case, the whole power. Okay, so this is 2 to the n minus 3, 2 to the n minus 2 plus 1 for all cases, right? When n bigger or equal to 4. Okay. Because when you go back and check proposition 13, the conjugacy class graph, still is a complete graph. It's a complete graph. And it has 2 to the n minus 2 plus 1 vertices. All right? So you have that times 2 to the n minus 3 edges. Okay, so similar to the one before. Okay, now theorem 30 is the Zagat index of co-prime graph of QD 2 to the n. And for this one is equal to 2 to the n minus 1 squared. 2 to the n minus 1 squared. Okay. I have time to actually write out the proof for this last one. Okay, so let's do that. Let me copy it here. Okay, so this one. Okay. Now, let me give you some work to do. Okay. Find proposition by proposition 17. Okay. Now, what is the co-prime graph of this? What is that? Who is fast? If you are in my class, I will bring some chocolate. Who is fast? You get the chocolate, you get the sweet. Make sure I get the right proposition. Proposition 17 is the co-prime graph of quasi-dihedral groups. It's isomorphic to a star graph. Okay, a star graph.
Star graph of K1 and 2 to
Okay.
power. Yes, that one.
2 to the n minus 1.
For n more than and equal to 4.
For n bigger equal to. Alright. Okay, so we have how many edges connecting to the identity element? And all other vertices of the graph. So you see N1 E of the graph. You have those many edges, 2 to the n minus 1. Okay, for this, right? Because they connect to others, and the rest of vertices, connecting the identity and the rest of vertices. And N2 of this is equal to 1. Okay, so you can generalize this actually. For the star graph, what is actually the Zagat index of the star graph in general? So you see the pattern here. You have this group, and then you have this many different definition of the graph, and you apply that group for that graph, and turns out it's something familiar, right? It turns out it's to be complete. It turns out it's actually a star. So in the beginning, if you already have this one general formula for complete or for star, then you can just apply. You don't have to rewrite all the proof, but it is very interesting to see the structure of your graph related to these different kind of groups. Okay, people might say, hey, why you want to calculate all this? The star graph is already there, the complete graph is already there. It's not just the result. It is how you can see from different structure of groups, these are different groups, you can get actually a common graph with some specific condition, with a different, some n maybe for this n, for these 3 different groups, you have the same graph, something like this, right? When you learn about group theory, you have isomorphism, right? So this group, if they are isomorphic, people have shown, I think that the intern also have that, right? If G and H are isomorphic, then their graphs are isomorphic. Can you go back? If you have 2 graphs that are isomorphic, meaning you can map the vertices and edges, are the groups isomorphic? No, right? The answer is not necessarily true in general, but you have to add some condition. And that is what we are doing in research. You want to get something satisfied, this some condition, but you need something extra, and you are the one that putting that something extra. And you say like, oh, I had to put this in. Why not? It's your it's your theorem. So put in until you get whatever you want to be satisfied. So these are some of the things how you relate previous researchers. And if people have done commuting graph like before, what about the non-commuting graph? It's just the complement, right? Now people come up with conjugacy class graph in which they change the vertices. I can change my vertices. I want it to be like the centralizer, something like this. If they have found the vertices to be conjugacy class, I want the edges to be different, right? I want the edges to be probably more complicated. See, like I mentioned, you need to create problem. People want to solve problem, but mathematician, they create problem. Okay. Some of the things are just, you know. Okay, so this is for this particular one. Okay, I have another hour for the lecture, right? Which is, let me see, which will cover the Harari index. Okay, that is the last topological indices for this particular lectures or school that I want to share right now. Okay, and for this third one, where is my phone? Okay, I have 4 minutes until our next break. You need to stretch again. Okay, in these 4 minutes, I want to see my students' face again. Please turn on your video for 4 minutes.
Ayo, on kamera.
On-kan kameranya. You are actually very, very lucky to be in this special summer school. You know how hard they have put in together different lecturers from different universities, and you can see, and like, we don't want to compare, but you are able to be here in between just like less than 2 weeks, right? Although I know it's very tiring to be online from like early morning until afternoon, but just put this in the list of your memory in your degree, right? You will never get this like after you graduate. You will miss actually.
Yeah.
Right, online. That's why because you are from like Brawijaya, right? UB, is it the name?
Yeah.
You see Ailangga. This is maybe your first time meeting your friends here, right? True? Yeah. So if you hide, sembunyi di belakang screen. I know some of you don't have enough data or not, but try to get as much. And I hope that all of you students, you keep in touch with your friends. Okay, when I retire, when Ibu Zahida retire, then maybe Dr. Idayu will replace me in the university in Malaysia. And then some of you will probably continue for masters, for PhD. Maybe you will be the one conducting this, right, Zahida? Conducting the
Yes.
summer school for
Sure.
you. Where you work, maybe you become dosen. See, you never know. You started from right now. Okay, actually, I want to see your face. And then, is it okay? Is it clear for the indices that I have shared this morning? Okay, I hope it's clear. It's clear. You have to show. This means clear, right? At least it.
Jempol.
Otherwise, I will think that only Nidia in the class and Zahida.
Jempolnya mana?
Sri Nurhayati, mana jempolnya? Iya, ini jempolnya.
Melayu juga jempol ya, Bro?
Tak, Melayu panggil ibu jari.
Oh, ibu jari.
Jempol tu Jawa. Ayu, you are not Javanese, right? Dr. Ayu?
Yeah, I'm Javanese.
Ayu Melayu. Okay, so we will take a break for another 10 minutes. Okay, then we will meet again for our last indices for Harari index in 10 minutes, 11 your time. Okay?
Okay, Prof.
All right, see you later in 10 minutes. Okay, so welcome back. In one way, it's quite comfortable, right? You just be in the comfort of home, but it's quite lonely. You are
Yes,
just by yourself.
that is true.
If you are given a chance, if I'm given a chance, I would want to come back to campus meeting my students. It's different, right? But
Yes.
this is the best we can do. So hopefully soon, it's not like the traveling, but it's the experience, it's meeting. That's why at least I can see Ibu Zahida's face, Dia's face. It doesn't matter if you smile or you just like, right? But it's nice for now until we get to eat in person. Hopefully, I can meet some of you in person one day. Okay, so the last, there are so many other. I will mention more names of the topological indices, but the last one that I want to share is the Harari index. Okay, after the class, maybe to complete the background of all the indices, I would suggest that you could do some literature review. Google, nowadays is very easy, right? Zahida, during my student time, I really have to go to the library, find books, even to connect to the internet from my house, I have to dial. Okay, now it's connected to the school. So we don't have WhatsApp, we don't have that, all those things many years ago. So nowadays, use that opportunity. Google about all these name of the indices, they came from the person who introduced them. At least we know more about this than just during the class. Okay, so again, we have for this Harari index, we need to have gamma to be a connected graph, and we want the vertices to be 1, 2 until n. Okay, so the Harari index H, or normally they just use this, or you can just write like the Harari index of a graph, gamma, but sometimes people just put H. It's a half, okay, it's a half sum of the sum elements, okay, d to the rij. Again, we want the index to be from 1 to n. But I have to, what is this? This is not just the distance between the two, there is the r, right? So the rij is actually the reciprocal. In Malay, we call it salingan, 1 over. Reciprocal, 1 over.
Balikan.
What is it?
Balikan.
Balikan.
Inverse.
Salingan, balikan. Reciprocal. All right. So this is 1 over the distance. Shortest distance, yeah? When I mentioned about the distance, is actually the shortest distance. If they are not equal, because if it's equal, it's 0, right? You cannot do 1 over 0. So you just put equal to 0. Okay. So this is the normal distance. It's 1 over. And so I had to pull the whiteboard from before and draw that graph. Okay, by now you must be remember already about this graph. System graph. 1, 2, 3, 4, 1, 2, 3, 4, 5. So this is just a simple connected graph, and we want to calculate the Harari index. Okay, so it's equal to that. All right. Okay, so H of gamma is equal to 1 over 2. I from what to what? 1 until 4. Yeah, 1 until 4. Okay, so how many times, Nidia, we want to calculate this? 4 times 4, right? 16 times. Okay, add up 16 pairs of IJ. All right. Okay, so if you want to write out, that will be, for example, the first one will be 0 plus 1 over 1, 1, right? 1, 1, 1, 2,
1, 3,
1, 3,
1, 4.
1, okay, plus
2, 1,
2, 1,
then 0, and 2, 3.
2.
Oh, okay. Mm,
Then
still continue. 3, 1, 3, 2,
3, 2,
0,
0,
and 3, 4. And then the last,
4, we can do 4. If it's 10, I'm not going to do 10.
yes, just etc.
For first one, it's okay. 1 of the, for
For
1,
1,
D, for
for
2,
2,
D,
for 3,
3, for 4, you don't do, you do.
0. Okay.
Now the distance, you can plug in all the distance. Yeah. Let's try not to erase. Okay. 0 plus 1, right? The distance from 1 to 2, 1, 1 to 3, 1, 1 to 4, 1. So you imagine if it's complete graph, right? It's all ones,
All 1.
all one. So you can easily get it. Then the second one is 2, 1, 0, 2, 3, 1,
1,
1,
2, 4, 2.
1,
2.
or 2. Yes.
There is not only one, because if it's not connected,
Oh, it's gonna be 2.
yeah, it's not connected, then it's 2. The others, they're all connected, right?
Yes.
So you will only watch out the 2, 4 and 4, 2, right? So you see the others, they are all ones. So you can go do it quickly. You don't have to do it like one by one. You just look at the only one that is this missing is the one you have to do 1 over 2. All right. So that will be the same thing, and you have 2 of this, right? You have 2 of this, you have 2 of this. Okay. So you will get this. Okay. I can do shortcut, yeah. Right. So this one is 6. This one is 5. Right. This one is 3. 3 times 2 is 6. This one is 2.5 times 2 is 5. 6 plus 5 is 11. So 11 over 2. So this is the Harari index for our particular graph. All right. Now we have to find the Harari index of the three graphs of the three groups. Okay, so in this lectures, we have found 3 times 3, 9 times all the indices. Wow, that is like so many results. All right, let me write down, and you can see it contains some kind of fraction. Yeah, from before you see they're all like just distances, they're like the number of degree, which are all integers. Right now, because it's the reciprocal, kebalikan. So that's why you see some fractions in this one. Okay, so I call it theorem 31. So H of the non-commuting for the, right, when n bigger or 3, non-commuting. Okay, this is equal to, I write down here, because longer, 1 over 4, 7n squared minus 9n plus 2, and on 1 over 4, 7n squared minus 16n plus 6. And you see why we get this. That is from the 1 over 2. Then you combine and so forth. So the non-commuting graph for the dihedral group need to be break up into 2 cases. And that is why we get this. So we have the case for the odd one, it's the multipartite graph, right? So you will see for the from proposition 7, I believe. If you remember, I write this last time. There is the n times of this. And the one n minus 1. So we have the independent set n minus 1. They are not adjacent, right, to each other. And we have n independent set, only one element. So we have the number of edges in the proposition. After that, proposition 10, we have 3n n minus 1 over 2 edges. This one with distance 1. Okay, this one is with distance 1. And we have n minus 1, n minus 2 over 2 with distance 2. So the reciprocal is 1 over 2. The reciprocal distance. The distance is 2, but 1 over 2. And the Harari index you can find by adding up the number of edges. And particularly, you add this up with this one. Yeah. Then you get to this one. So it's pretty straightforward for that particular one. For the other one, for the case n is even, the graph is still multipartite, but this one is 2, 2, 2, and minus 2. So similarly, you have 3n n minus 2 over 2 edges with distance 1. This is n minus 2 for this one. Then n minus 2 and minus 3, right? With reciprocal distance 1/2. So you add up all this reciprocal and you will get exactly this. So this mainly come from the fact that the non-commuting graph of the dihedral group is multipartite. Okay, so you understand how the graph is and separate and find the edges. For this one, I think it's much simpler than the index. Before, in in which you have the N1 and N2. That's pretty complicated, right? Okay. Now, for the next theorem is the conjugacy class graph. Right? The conjugacy class graph when n bigger or equal to 3, n is 4k. Then we have this is equal to n plus 2 over 8. Right? Okay, now why we get this? The conjugacy class graph of the dihedral groups in the case n and n over 2 even is complete. Okay, so this is a complete graph of n plus 2 over 2 vertices, right? So since it's complete graph, the reciprocal distance is just the distance, right, between the two vertices, right? So by definition of the Harari index, we have just the distance. So we have how many? N plus 2 over 2. I'm sure, Nidia, you will remember after this how many edges when you asking about the complete graph, right? So you see the formula becomes the formula for the Wiener index because the d to the r of ij, which is 1 over the distance is, if this is 1, right? It's a complete, the shortest distance is 1, it becomes the same, right? It becomes the same. So it's similar to the Wiener index because it's complete. All right. Now next is the Harari index. Just now it's 32. Missing number, theorem number. Just now it's 32. Now it's 33. Right? We go to the co-prime. Okay. So still for the dihedral group, and n bigger or equal to 3 and odd. Okay. Now this is equal to 3n squared minus 1 over 2. All right. The next one is when we have two cases, right? This next one is for the case n equals to 2 to the k. Okay, this becomes theorem. This is n plus 1 to n minus 1. Now you see the half everywhere because of the formula of 1 over. Okay. Now, if I ask you to prove this, then you know the step already, right? You look at the graph, then you look at if it's multiplied, it's like this. If it's complete, it's easy. Don't write easy in the proof because sometimes students write the proof is easy. No. Okay, next is the non-commuting for the next group, yeah? Theorem 35. Non-commuting for the generalized quaternion. And this is out to be 7n squared minus 8n plus 3/2. Okay, this is for order for n bigger or equal to 2. All right. Now theorem 36. This is for conjugacy class graph of generalized quaternion. For this one, we want non-commuting. I have that. Okay. This is for conjugacy class graph for generalized quaternion group and bigger equal to 2 and even, yeah. And this is equal to n plus 1 over. You see, if you put together all these different kind of indices for this different kind of graph for these groups, you will see some similarities because in some cases the indices are the same for some graph because of the formula, right? Just now, as I mentioned, for complete graph is like this, and the summation, double summation becomes equal because the distance becomes equal for the complete case. Okay, the next one is for the generalized quaternion groups for the case n2 to the k minus 1. Okay, for the co-prime graph, for the co-prime graph. So H of co-prime graph for the Q point. So 4n squared plus n minus 1. Now, how do we get to this? The co-prime graph of the generalized quaternion group is a complete bipartite graph. Okay, so the co-prime graph of the generalized quaternion group is the complete bipartite graph. And this is the figures. Okay, for this one. So we have this many independent set of vertices. They are not adjacent to each other. So this is actually we call earlier as a star graph, right? So the star graph, the complete graph, you can show this in general in which which one of the vertices they are all equal to 1 is the when you put what is it, n is 2 to the k plus 1 vertices, right? 2 to the k plus 1 minus 1 is the number of 4n minus 1. Okay, the generalized quaternion group of this one. So you have the number of edges with the distance is all 1, and then how many with reciprocal distance 1/2. So you can add up the number of edges for that particular one plus the reciprocal distance. The one that I gave is also quite direct in the proof that I give in your notes. So you can figure it out from the star graph. Okay, now next would be the non-commuting graph for the third group, quasi-dihedral group. All right, so we have the last one, 38, 39, 4. Okay, so for this one, we have to change the QD to the okay. The first one is the non-counting one. Okay, this is 7. Yeah, consider 2 is quite complicated. The graph. 2 to the 2n minus 4 minus 2 to the n plus 0 into 2. Okay. For this one, when we have the different little bit, right? The condition and with order, yeah, n bigger to 4. Okay, this is 2 to the n minus 3. 2 to the n minus 2. This also highly dependent on the graph of this one. You see 1/2, the distance. Some of them is 1/2. They are embedded in 2 to the minus, right? Because you don't see it, but it's inside the negative here. Okay. And then the third one, all right? The third one is, I'm missing the graph in the name. You can add the G in the graph. The Harry index of co-prime graph for QD2 and theorem 40. Yeah? So this one is equal to 2 to the 2n minus 2 plus 2n minus 2 minus. Okay. Let me just give the proof of this one because we have the time. Okay. Okay, I have to refer to the proposition for the co-prime graph. The co-prime graph, if you have your notes, go to proposition 17. Proposition 17. Proposition 17. The co-prime graph of the group G, considered group, is equal to the complete bipartite graph 1 to the n minus 1. Okay. Then there are, okay, for this one, an independent set of the identity element of G for this one, and independent set of 2 to the n minus 1 vertices, okay, which are not adjacent, right? Okay. So this one is actually the star graph, right? Sometimes we call this star graph. of 2 to the n vertices. All right. Okay. Hence, it has 2 to the n minus 1 edges, okay, in which the distances of all vertices are 1, right? So there's one set in which this is like a complete one, in which of vertices, and then there's another one, and there's another one. So you have this many. Meanwhile, there are 2 to the n minus 1 times 2 to the n minus 2 over 2. This one has to ask Nidia how I get this formula from the complete graph, which have reciprocal distance half, right? For the complete graph. Therefore, now we want to calculate h of the coprime graph of q d n equal the number of these edges of this q d n. Just add that up to this, right? 2 to the n is 1, 2 to the n is 2 over 2. So you can plug in, we have 2 to the n minus 1 for this number of edges plus 1/2 of this whole thing. And finally, simplify, then we get 2 to the 2n minus 2 plus 2 to the n minus 2 minus. So this is how you get the Harari index of the coprime graph of the quasi-Dahiri group of order 2 to the n. This is actually directly by using the definition. So you see, you can come out with a general formula without even probably referring to literature review, although it's already there, right? What is the Harari index of the complete graph? Okay, before you refer this, I'm sure all of you can now think of how to prove and calculate or compute some simple index of certain graph in general. Like for complete graph is like this, for star graph is like this, right? Okay, so I want to share a little bit about, this is what I want to share, Bu Zahida, about the topological indices. Not only the topological indices, but I have also shared different type of groups. Like Nidia said, you have not really studied about this in particular, right? Dihedral group, yes, is very common. Quaternion also, I saw Dr. Intan, Bu Intan already mentioned about the generalized quaternion, also with the presentation of the group. But this one probably is not that familiar. And there are many others. So there are many also future works that can be done to find. Let me see. Where is it? Let me write here. Actually, yesterday, I think, Zaida, or this morning, I cannot even remember. I mentioned if you want to collaborate, right? If you have someone, if you are from Mailanga, your Dawson is here, some of you, we can actually collaborate, and I can become like we have like in UTM, we have external co-supervisor for our students.
Oh.
So maybe I have a student coming with me. I can say, okay, why don't you co-supervise with Zahida from there? Because before, like Dr. Ayu here, she has an external co-supervisor. You know Prof. Ahmad Irfanian, right?
Yes.
From Ferdowsi, yeah. So he's actually Dr. Idayu's external co-supervisor. We can do that. We have from Ailanga, we have from Gajah Mada, we have from, so this kind of collaboration that we can do. And a good thing, if you remember, I share about the mobility activity in UTM. I had quite a number of students who come here for 1 month, 2 months, 1 semester to just do short research attachment. At least you can become, you are like Ailanga student, right? You can just come, and because we are partners. The one that I share with you my slide. Oh, I will pass you the slide. Ibu Zahida, you can pass to the students the slide about UTM. The one that I upload is all about the notes. The one about introduction to UTM, I will pass later, or I will pass to Ibu Zahida. It's not part of the topological indices. That's why I didn't put in the. But this is something that you can do also. You can come and be our UTM student for a short while, right? At least you can travel abroad. Hopefully next year, really when it's safe to travel. If you don't get the opportunity during your study, when you become a docent yourself, to all these students, you are still welcome. If you need to go to any other universities in Malaysia, I'm part of also Malaysian Mathematical Sciences Society. So I can connect you with whoever from other universities in Malaysia. Back to this work. Okay. So I mentioned about just these groups, right? You have many others that we haven't even looked, many others for groups. There are many other type of groups that people have not found the graphs, right? So this is what you can extend to the same graph, the same 3 graphs for different groups, or come up with a new graph for these 3 groups, right? And there are many other topological indices. Okay, political indices that have not been computed for other graphs or groups. Yeah, because the one that they compute is all the graph that they have from the graph theory, right? So this one, there are other, which is called the Prendick index. Okay, Dr. Ibu Zahida, you mentioned about the project you have. Which index is it?
You already talked about it.
One of these, yeah. Okay. Schultz index, we have this. We have degree distance index. We hope actually to come up with a new index, but it didn't get to it so much. So if you think like, why don't you create this new formula to, like, we have already the reciprocal, we have the square, right? Who knows, maybe there are others, the cube and some others. So this, from this, you can also find some properties of these indices? What are probably in general formula for the maximum or minimum value, something like this, yeah, for this one. And you can make your group larger, right? For these groups, why not, if you have G and H, two groups from whatever groups that we have, why not we try with the direct product of these groups, right? It becomes larger. What happened to the graph? And with that particular graph, whether it's connected, if it's connected, then you can probably find the topological indices. So these are just some other things that we can do, but to make sure you do the background check if people have done it or not. So these are just to give some ideas about further research that you can do. But I think I already give you just the basic, like we learn in class, you learn about groups, you learn then, but what is actually research, right? Research is something that nobody has done. I mean, the novelty, but based on whatever results, whatever the literature review that people have done, these are the steps. So by giving you some examples, you can see the pattern. So it's always coming from this group. You got this graph, and from the form of the graph, you can compute all the indices. Some of them you can say that it's probably very, very similar. Some of them computations are different, but once you get used to it, you get used to the definition of different indices, then you have the idea of computing. I don't say it's really difficult or cannot be done. Yes, it can be done. The first time, I'm sure whoever is doing research is very, very hard. You imagine the one that I give you when I give you the definition, like what is N1, N2, right? Now, giving example, it's getting, you just imagine if you have to sit at home and you have this one paper, you try to understand by yourself. Or you come to class like this with the whiteboard, and then you do this together. Okay, so Ibu Zaida, that's it for my lectures. We have after this a break, and then after your lunch, right? If I'm not mistaken, then we will have a tutorial session.
Yeah.
Yeah. So I will upload the question like we did in the first class. Okay. And I'll give you some time. I don't want to bother your lunchtime. You want to eat quietly, happily. And then during our tutorial, maybe I give the chance to Dr. Idayu to speak, but give you some time, and then we will share. This is actually how your understanding of the class is tested, right after, whether it is okay to not being able to get the right answer, but at least we can see the steps. Okay, so I will give you the question later and write again, and then you have the time to try like the first class, right? I will like you hear from maybe Dr. Idayu. Then I can write for her. I can write and you can teach from there. And then the final hour will be tugasan, right, Zaida? How is it done for that one?
The lecturer just upload to the
question
classroom, and then we don't need to join the Zoom.
Okay, so
the student do the like homework.
Okay, so it is like homework, and you are given that 15 minutes to try it.
Maybe the due date usually tomorrow.
Okay.
After the lecture, upload the assignment.
Okay, I pass to you for that one, yeah,
Yes.
Zaida. I just pass to you the question, and then
Okay.
you upload. We don't have to be in this Zoom, all right? And you have until tomorrow. I
Yeah.
think you are given that 15 minutes to probably look. If you can finish, then that's done. You don't have to wait until tomorrow.
Yes. Sure.
The other friends, they are free. Okay, let's go into our own Zoom and try this. Okay, so I will see you in 1 hour or so.
Wait, Lydia?
I should
Uh,
ask Lydia before I exit.
Yeah, before
okay.
Professor Lim.
Okay, Professor. Before the professor leave,
Yeah,
there will be a certificate given from the head of the event, Dr. Zaida. Doctor or what? What's the title? I don't remember. For Bu Zahidah lah.
Hmm.
Yeah, from Bu Zahidah to Professor Nisa, the certificate will be given as a symbolic appreciation for Professor Nisa participating in IndoMS summer class as one of the lecturer. So the certificate gifting will be captured in a photo session. So for for anyone responsible, please take the photo.
Yes.
Thank you very much, Professor, for sharing the knowledge.
Okay.
Okay. Okay. On three, get poster. 1, 2, 3. Okay. Done.
Oh, tak ada freestyle ya? I want to.
Freestyle. Okay.
Maybe
1, 2, 3. All right. Done.
Sorry about last time because I didn't expect that you will close it like really official, and then I see the
It's okay.
I see like Oniza already left the Zoom. Sorry about that. Yeah. So
Okay.
we will meet again in
Okay.
1 hour plus. Okay. Enjoy your lunch. See you later.
See ya.
Assalamualaikum.
Waalaikumsalam.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay, so thank you so much for Professor Nisa for the lecture at this session. Thank you so much. And because it's 13 minutes before 12, we'll be having break for about an hour. And all the participants are expected to be present in this Zoom at expectedly 10 minutes, please. 10 minutes before 1 p.m. Indonesian West time, because the lecture and the tutorial session will be given by Dr. Idayu, right? Yes. Okay. So in the end, I will also, as the moderator, will say Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Bye-bye.
Ya, terima
Bye.
kasih.
See you later.
Host can end the Zoom, please.